Okay, section 11.3 is on combinations, working with Pascal's triangle and the binomial theorem. So Pascal's triangle is a tool that's used in math and in chemistry and other sciences. And it's used to find, well, it's used for a lot of different things, but we're going to look at is how it is used to find coefficients for binomial expansions. So Pascal's triangle is based on this. If you start at a triangle, if you start at the top of a triangle with a 1 and bring down your 1's here, the 1's you'll notice come down all the way. And what happens here is to find the middle term, you add these two. So 1 plus 1 gives me 2, so I put that in the middle. I have 1 and 2 beside each other. 1 and 2 give me 3. 2 and 1 give me 3. My 1's come down. So my next row, I would have a 1 and a 1. And then I would do 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. And then, of course, my 1 that came down. My next row would have my 1 and my 1's on the ends, and then it's that adding. 1 and 4 is 5, 4 and 6 is 10, 6 and 4 is 10, 4 and 1 is 5, and then my 1. The next row would be my 1's on the end. 1 and 5 is 6, 5 and 10 is 15, 10 and 10 is 20, 10 and 5 is 15, 5 and 1 is 6, and then my 1. And I could continue this pattern forever and ever and ever, really. What we find here is that these values we call our n values. If we take a look at what's happening here, if this is my row 1, my row 2, 3, 4, 5, 6, and row 7, the number that is in front here is always, or the number after the 1 is always 1 less than my row number. So my 7th row, my coefficient is 1 less than the row number. This relates to our combinations, in that if you were to take whichever row, let's do this 6th row here. If you were to look closely at it, you will see that you have actually a pattern following that's using combinations. So if I take my 1, my 5, my 10, 10, 5, and the 1. So although this is my 6th row, if I were to use the pattern 5C0, 5C1, 5C2, 5C3, 5C6, and then, oh, did I miss one? That should be 5. 0, 1, 2, 3, 4. There we go. And then 5C5. Oh, I'm just going to move that out of the way. If you were to calculate this, 5C0 or 5 choose 0 is a value of 1. 5 choose 1, I'll do that one as our expansion that we did in the last section. So 5C1, if I use my formula, and remember my formula is n factorial over r factorial times n minus r factorial. So that would be 5 factorial over, my r is a 1, so 1 factorial times 5 minus 1 factorial, which is 4 factorial. So that is equal to 5 factorial over 1 factorial is just 1, so that just equals, if you calculate it out, it equals 5. And if I look, my 5C1 is a 5 there. Same thing then if you did it for 5 choose 2. We have 5 factorial over 2 factorial times 3 factorial, and when you reduce it down or solve it, it's going to give you a 10. So what's happening here is this was my sixth row. It was my sixth row, but I used a 5. And that's where the pattern comes in for this. Whatever row number you're looking for, the number that's going to be your n is going to be 1 less than your row number. Okay, so my 5 choose 0 there. This was the number in front, my n is 1 less than the row number. And my r then is 1 less than the term we want to find. Oops, that skipped a couple of words there. Is 1 less than the term we want to find. So if I'm looking for my third term in the sixth row, to find that out, so third term in the sixth row then is going to be 1 less than that and 1 less than that. Remember, this is my n, that's my row, and this is my term, so then this would be 5c2. So my third term in the sixth row, 1, 2, 3, 5c2. Okay, so that's one little kind of trick thing that you have to remember. When you're finding a term, then you need to know what row it's in, do 1 less than the row and 1 less than the term, and then you can use your combination formula to find it. Okay, so example 1 here says, what is the second number in the 30th row? So my term is 2, my row is 30. So then that means that this is going to be 29, choose 1. Because I used my n is equal to 30 and my r is equal to 2. So in order to calculate, it's 30 minus 1, 2 minus 1. So 29c1, if you put that in your calculator, if you just remember anytime it's the number choose 1, it's just going to be that number. So what is the 7th number in the 50th row? So my n is equal to 50. My r is equal to 7, so if I subtract 1, this is going to be 49, choose 6. And in your calculator, that gives you 13,983,816. So you can see where remembering this simple term finder, I'm going to call it, because it's not really the term formula. We're going to do something, or well, yeah, we'll just call it the term finder. It's always going to be n minus 1, choose r minus 1. So if it's a small one, if it's just something, say, in the third row, you could easily use Pascal's triangle to solve for it. But when you're getting into ones where in the 50th, you don't want to have to do this another 43 times, going 1, 1, 1, 1, add, all in between there. Okay, I'm going to skip over these pathway problems. You're really not going to come, other than a textbook question, you're probably not going to be coming up to them. If you want to know how to do them, then you can come see me separately and I will go over them with you. So there's, I think, a full page of these here. Okay. So we're going to look at binomial power. So we're going to look at the expansion of a plus b to the power of n. So if a plus b is to the power of 0, this is just going to be a 1, because anything to the power of 0 is a 1. A plus b to the power of 1 is just a plus b. A plus b squared, then if you think about that, this is saying a plus b times a plus b, And you can write it out and FOIL it, or you can do our shortcut method, which is square the first term, 2 times the terms, so 2 times a times b is 2ab, and then square the last term to get a b squared. So a plus b cubed then is a plus b times a plus b times a plus b. So since we've already calculated a plus b squared, then really what we could do for this one is just multiply this by a plus b again and write our answer in the bottom. I'm not going to work it out for you, I'm just going to give you the answer, but that's all you would do. You would go a squared times a, 2ab times a, b squared times a, and then b times a squared, b times 2ab, b times b squared. So your answer for that then is, in order, a cubed, 3a squared b, plus 3ab squared, plus b, and that should be a b cubed, I believe. I think I have a b squared on my page. I'm just going to pause here and check my math real quick. Yeah, okay, I'm good. That was just a typo on my page. So a cubed plus 3a squared b plus 3ab squared plus b squared. So then if we were going to go one more time and multiply again, because this would be a plus b times a plus b times a plus b times a plus b. So a plus b multiplied together 4 times. So if we were to multiply this by a plus b again, then we would get a to the 4th plus 4a cubed b plus 6a squared b plus 4ab squared plus b to the power of 4. Okay, so that's just by multiplying each of those terms by a and then multiplying by b and collecting my like terms. So what we notice here, and if you can see, it's almost making a triangle of its own. We have, if you think of Pascal's triangle, it goes 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, right? So if you take a look at this, it's following that pattern. My terms are, first I've got a 1, and then I got a 1 coefficient and a 1 coefficient in the a plus b. I have 1, 2, 1 in that row, 1, 3, 3, 1, 1, 4, 6, 4, 1. So it's following that pattern. So that works for my coefficients. So my coefficients follow Pascal's triangle, which we can use that our term finder, if we want to call it that n minus 1 c r minus 1 to calculate that, if it's above a few simple rows. What else you might notice here is in this one, my powers in this row here were a 1 and a 1. In the next row, I started with an a squared, and then I went, I'm just going to use another color here. I started with a squared here, and then I went to a to the power of 1, and then basically a to the power of 0. In the next row, I started with, I was a cube here, so I had a cube here, then it was a squared, and then it was a power of 1, and then basically a to the power of 0. So each row that I go, my a value is decreasing, or my a power is decreasing each term. A to the 4, a to the cubed, a squared, a to the 1, no a. So power of a is decreasing. Whoops. Or it's going to have to do a catch up. We'll see if it'll catch up each term. We've got a Christmas tree going on here. Okay, we'll just wait a second for it. See if it'll catch up. So my power of A is decreasing. Oh, now it's green. Each term. So then let's look at what's happened to B. So it was a 1 and a 1 in here. I'm going to use, maybe I'll use red for my B's. So in the first term here, I had no B. Oh, I better go to the second row here. No B, 1B, 2B. No B, 1B, 2B, 3B. And if you notice, it's always my first AQ, or my first A power matched up with whatever this power was, and my last B power matches up with whatever that power is. So in the fourth row, I had no A, no B, 1B, 2, whoops, there should have been a squared there. Did I miss something? B1. Yeah, there should have been a squared here. 2, 3, and 4. Sorry. So I had 2B, 3B, 4B. So my B powers are doing the opposite of the A's. They are increasing every time. So the power of B is increasing with each term. Okay, and my coefficients are following that Pascal's triangle. So my coefficients then are following a pattern of this. So this is for the coefficients. It's going NC0, and then it's NC1, NC2, and then NC3, all the way down to NCN. So if you remember on that other page here, let me put back a couple pages. Whoop, one more. It was 5, 0, 5, 1, 5, 2, 5, 3, 5, 4, and then it went to 5, 5. So because whatever my n number is here, I have to end up with that n number as my last term. So it has to be, always will be NCN as your last term. So let's take a look at how we can use this, what we know here, to expand A plus B to the power of 5. So my n here is a 5. So I'm going to do my my terms, coefficients in the purple, so you can see that what I'm doing there. So for this one then, my term needs to be n, not, whoops. My n is a 5, so I start at 5C0 and leave a little space here, plus 5C1 plus 5C2 plus 5C3, excuse me, plus 5C, whoops, got my subscript, 5C4, and then I end at 5C5. Because I can't choose more than I have, right, for my combination, so that's why it ends at the 5. So then following the pattern here for my first term values, so let's say for my A values, my A has to decrease with each term. So I start with the highest power that I can have, so because n is a 5, this is A to the 5, so then this would be A to the 4, A cubed, A squared, A to the power of 1, A to the power of 0. My B, we said, has to increase with each term. So it starts small and then goes big. So it always is going to, the first term your b, or your second term here that's in there, is always going to be starting at 0. So then it'll be b1, b2, b3, b4, b5. So if I put all that together, 5 choose 0 is just 1. So this equals a to the 5th, plus 5 choose 2 is 5. So that's a to the 4, b, plus 5 choose 2 is 10, a cubed, b squared. 5 choose 3 is 10, a squared, b cubed. 5 choose 4 is 5, a, b to the 4th. And then down to 5 choose 5 is just 1. So that's, whoops, a is gone because it's just a 1. A to the 0 is 1, b5. Okay, so that works nice when you have just a plus b. Nice little terms with nothing in front of them, no other value, no coefficient with them. So the next one here is expanding it when we have something else in there. So instead of having a nice little x and a 1 even, we have 2x. So this is my a value, this is my b value. So I'm going to do the exact same thing as I did in the other row, or in the first example there. I'm going to expand by finding my coefficients and then applying my exponent to the a and the b. A is decreasing from the beginning, b is increasing from the beginning. So for this one, it's a power of 4, so I'm going to start at 4 to 0. My a is the same, this a here is the same as a 2x, so that means it's going to be 2x to, whoops, not 2, 4, 2x to the power of 4. And if it helps you, write that b power, so times 1 to the 0, plus 4 choose 1, 2x cubed, 1 to the power of 1, plus 4 choose 2, 2x squared, 1 squared. Plus 4 choose 3, 2x to the power of 1, 1 cubed, plus 4 choose 4, 2x to the power of 0, 1 to the power of 4. So if I evaluate these, 4 choose 0 is just 1. 2x to the power of 4. So remember, when you're working with exponents, you have to apply the exponent to both terms. So 2 cubed is 16x to the 4. 1 to the 0 is just 1. Plus 4 choose 1 is 4. 2 cubed is 8x cubed. Times 1 to the power of 1 is just 1. Plus 4 choose 2 is 6. 2x squared is 4x squared times 1. Plus 4 choose 3 is 4 times 2x times 1. Plus 4 choose 4 is 1 times 2x to the power of 0 is just 1 times 1 to the 4th, so it's just a 1. So now if I finish my simplifying, this is 16x to the 4 plus 32x cubed plus 24x squared plus 8x plus 1. One thing you might also notice as we're going through these, my coefficients, or sorry, my powers, 5 and 1 is 5, 4 and 1 is 5, 3 and 2 is 5, 2 and 3 is 5, 1 and 4 is 5, and 0 and 5 is 5. So what you're going to notice is when you're expanding these, your powers of your terms always have to add up to equal whatever the power was in the question. Okay, so let's try another one. X minus 3 to the power of 4. Actually, I'm going to skip that one because it's a pretty basic one. Let's try 3x minus 2 to the power of 4. So 3x minus 2 to the power of 4. So this starts at 4, choose 0. My a value is a 3x, so it's 3x to the power of 4. My b value is a negative 2, so that's negative 2 to the power of 0. Plus 4, choose 1. 3x cubed, negative 2 to the power of 1. Plus, whoops, that needs to be a subscript. 4, choose 2. 3x squared, negative 2 squared. Plus 4, choose 3. 3x cubed, negative 2. Whoops, that shouldn't be a cubed, it should be a 1. Negative 2 cubed. And then plus 4, choose 4. 3x to the power of 0 times negative 2 to the power of 4. So another thing you might notice here is your b exponent is always matching your r here. So this was a 1, this was a 1. This is a 2, so my second exponent is a 2. 3, 3, and so on. So 4, choose 0, of course, is 1. 3 cubed to the power of 4 is 81 times x to the power of 4. Negative 2 to the power of 0 is just 1. So plus 4 times 27 x cubed times negative 2 plus 6 times 9x squared times 4 plus 4 times 3x x times negative 8. And 4, choose 4 is just 1. 3x to the power of 0 is 1. Negative 2 to the power of 4 is a positive 16. So if I finish my simplifying here, 81x to the 4th plus 4 times negative 2 is negative 8 times 27. So this becomes not a plus, but a minus 216x cubed. So the next one, 6 times 9 times 4 is plus 216x squared. Oops, I shouldn't put my sign until I do my math. 4 times negative 8 times 3 is negative 96x, and then plus 16. So that is that expanded. Okay, I'm going to skip example C. Again, if you want any of these done, then just come see me and I'll do them, but it's the same idea. Okay, so let's see what we've figured out here. So if the previous pattern in the exponents and coefficients of an expansion of binomials is called the binomial theorem. So we discovered a few things here when, and I'll just flip back to this one where I have all of the colors. We discovered a few things as we were expanding these. Our exponents always equaled whatever the n was. Our a-term exponent starts out at 5, or at whatever the n is, and then goes down 1. And our b, or the second term exponent, starts at the r value, whatever the r value is in the first term, and then is increasing by 1. So it's n minus 1 for the a terms, and r plus 1 for the second terms. Or it's just matching whatever the term number is. So it's first term is 0, not matching it, it's 1 less than whatever the first term number is. So if we make that into kind of a nice expansion theorem type thing, what we found out is we had our first term, and I'm just going to write it up, starting over here so I can use up my space. was at NC0, a to the n, B0, plus. The next one was at, I kind of wrote that, spread out, NC1, a to the n minus 1, b to the 1. Or you could also write it as this was r, and then it was r plus 1, and so on. But you can, that one you can just increase by ones, and it'll work for you too. So then the next one was plus nc2 a to the n minus 2 b squared, plus nc3 a to the n minus 3 b cubed, plus nc4 sorry, I just lost my train there, a to the 9 n minus 4 b to the 4th, plus, then I'll go all the way down to the end. It's going to be n, choose, that should be plus, n minus 1. So it's almost the last term, a to the 1, b to the n minus 1. So that's where that helps you remember that that needs to match. And then finally to n, c, n, a to the 0, and b to the n. So if I take a look at this, NC2 is really my 1, 2, 3 is the third term. So this value is always 1 less than the term value you're looking at. And remember, the n value in front is 1 less than the row you're looking at. So our term formula is, our term is equal to k plus 1 equals nck, so n choose k, a to the power of n minus k, b to the k. So what that is saying is if you're looking for the 7th term, so that would, sorry, 7th term, so then that would be actually 8 that we're looking at, so that would be 7 plus 1, so that's the 8th, would be nc7 times n minus 7 b to the 7. So remember, this and this always match, and if you look at this, in my pattern here, this was minus 1, 1, minus 2, 2, minus 3, 3. So it's just subtracting that value, and whether you use r or k doesn't matter as long as you can keep their what they need to do straight. It's always going to be the difference between those. So that's your term formula. And if you can't remember that, then just always remember that your term is always going to be, if it's asking for the 8th term, then you're actually going to look for your r value, or in this case they call it your k value, being 1 less than that. Third term meant we're looking at the 2 for the r. 8th term means that we're looking at the 7. Okay? Okay, example 3 here. And these ones I'm just going to pick and choose a few to do because there's a lot that repeat. What is the 10th term of 1x minus 2 to the y? So my term formula is t is equal to k plus 1 equals nck a to the n minus k b to the k. So my n that's my n. I should write these in. So n is equal to 12. My a value is equal to 1 over x. My b value is equal to Where am I? Negative 2y. So since this is my term formula, t to the k plus 1 is equal to, in this case, 10. That's what I'm trying to find. I'm trying to find, sorry, my 10th term. So if you remember when we're doing logs and when we're doing exponents, you can drop the common thing and just solve from there. So this would be k plus 1 is equal to 10. So k is equal to 9. Or just remember that when you're substituting in your k value is just going to be one less than the one you're looking for. So if I substitute in here, then this is going to be, my 10th term is going to be 12, choose 9, a to the 12 minus 9, b to the 9. So now I'm going to, I should have substituted in there, but I'll do it in another step. So this will be 12, choose 9, a was 1 over x, 12 minus 9 is cubed, my b was a negative 2y to the power of 9. 12 choose 9 is 220. This is 1x cubed times negative 2y to the 9 is negative 512y to the 9. So if I put this all together, it is 220 times negative 512, so negative 112,640 y to the 9 all over x cubed. Okay, let's try one more. So the 6th term of 3x minus 2y is equal to 9. So my tk plus 1 here is I'm finding the 6th term. So my k value is equal to 6 minus 1, so that equals 5. My n is equal to 9, my a is 3x, and my b is negative 2y. So using my formula then, this equals, excuse me, I yawned, 9c5 or 9 choose 5. My a value was 3x to the power of n minus k, so n minus k is 4. My b was negative 2y, and that has to equal to the power of k. Okay, now I didn't actually calculate mine out past that, so on your calculators you can just do your 9 choose 5, find that. 3 to the power of 4, I think that's 81, x to the 4th, and then negative 2 to the power of 5. That 32 or 64, I can't remember. Multiply them together and you'll get your answer. Okay, 10th term, I'll just set this one up too, and then you can solve it through. So my t to the k plus 1 is equal to t to the 10, so k is equal to 9, a is equal to 2, b is equal to negative y over 2, and my n is equal to 10. So this will equal 10 choose 9. My a value was 2 to the 10 minus 9, which is 1. And my b value is negative y over 2 to the power of 9. Oops. Throwing stuff around here. Okay, write the first 4 terms of the binomial expansion for the following. So my first 4 terms then, my n is equal to 13. my a is equal to x and my b is equal to 2y. So for my binomial expansion, if you flip back to the 4th page, we had our little pattern that NCOA to the n, b to the 0, and then it continued on there, plus NC1, a to the n minus 1, b to the 1, plus so on. Okay, so that's the pattern we're going to follow. So my n is a 13, so this is going to start at 13, choose 0. My a is x to the power of n is 13, times my b, which is 2y to the power of 0, plus 13, choose 1, x to the 12, times 2y to the 1, plus 13, choose 2, x to the 11, 2y squared. So I want the first 4 terms. I've done 1, 2, 3. So remember, your term is always 1 less than your r value. So plus, not n, that should be a 13. Choose 3, x to the 10, 2y cubed. Okay, and I didn't calculate these out. You can do those in your calculator quick enough to find 13, choose 0, and 13, choose 1. So, well, 13, choose 0 is just going to be 1. 13, choose 1 is 13, and so on, and so on, and so on. Okay? So for 2x minus y is equal, or 2x minus y over 15. So my a is 2x, my b is negative y, my n is 15. So this is going to start at 15, choose 0, 2x to the 15, negative y to the 0, plus 15, choose 1, 2x to the 14, negative y to the 1, plus 15, choose 2, 2x to the 13, negative y squared, plus 15, choose 3, 2x to the 12, negative y cubed. And then same thing, you can go on your calculators and find those out. So some of the patterns that we've noticed for the following. Okay, a to the 4, 4a cubed b, 6a squared c, 4ab cubed plus b to the power 4. So we notice from here that our a power starts at n and decreases each term. We notice that the b power starts at 0 and increases with each term. We have also noticed that our powers, when we add them up, have to equal the power of the original. And I'm just going to put the questions power. Okay, so the sum, the powers of the terms are the sum of the question. Actually, that should be the sum of the powers of the terms equal the question's power. And then our coefficients. Well, that should be capital P because that's his name. Pascal's triangle, or the NC0, NC1, NC2, and so on. Okay, next example says, for 2x minus 12, determine how many terms are in the expansion. So we know that if there's 12 terms, then there's always going to be one more term than power. That should be a than power. So this one would have 13 terms. Find the middle term. So there's a way of finding our middle term. If there are 13 terms, then our middle term is going to be the one that will have exactly the same amount of terms on one side and the same amount on the other. So our middle term is always going to be the number of terms you have plus 1 and divide that by 2. So if I have 13 terms for this one, I have enough room here. So I've got term 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. My middle term then is going to be 1, 2, 3, 4, 5, 6. If I go 6 this way, 1, 2, 3, 4, 5, 6 this way is going to be 7. That's easy enough to find when you have 13 terms. But this is where this middle term formula comes in handy, because when you have 67 terms, you don't want to be writing out your numbers to 67 and then figuring it out in between. So it's just as easy to go 67 plus 1 divide by 2. That's going to be your term number. So for this one, if I did that, my number of terms for this expansion here was 13 plus 1 divided by 2, which is 14 divided by 2, so that equals 7. So now if I want to find the middle term, and in this case the 7th term, I guess I did write a little bit big here. So what I'm doing then is my term formula. I want my 7th term, and I know that that's what I use. Term 7 is equal to tk plus 1. So that means 7 is equal to k plus 1. So 6 is equal to k. So using then my term formula, I know my n is equal to 12. My a is equal to 2x in this one. And my b is equal to negative 1. So my term formula said nck times a to the n minus k, b to the k. So 6 is equal to k, n is equal to 12. So this is going to be 12c6 times, my a value was 2x, n minus k, so 12 minus 6 is 6, negative b to the power of k, which is 6. So this equals 924 times 2 to the power of 6 is 64, x to the 6, negative 1 to the power of 6 is going to be a positive 1. So this equals 59,136 x to the 6. So what you'll notice though is, what if my power was a 13? Can I find a middle term for 13? Or for a power of 13? So if I did this for 2x minus 1 is equal to 13, and I should check. No, okay, I'm good. So then that would mean I would have 14 terms. If I use my middle term formula, this would be 14 plus 1 divided by 2. So 15 divided by 2 is 7.5. So if I change this to 14, I don't have a 7.5 term. I have a 7th term, and I have an 8th term. So you can only do middle term or find a middle term when you are working with an even power. So you can only find the middle term when you have an even power. So that could be kind of a trick question on your assignment or on a question on your exam. So if we determine the middle term of the expansion, 2x minus 13y to the power of 14. Okay, so my n here is 14, so my middle term is going to be 15 plus 1 divided by 2, so that is going to equal 16 divided by 2 is 8. So I'm looking for my 8th term. So that means T8 is what we're looking for. So that means my K is going to be 7, because it's always one less. So then using my expansion here, my A is equal to 2x. I guess I could write this all beside it here. My A is equal to 2x, my B is equal to negative 3y, and my N is equal to 14. So this is going to be 14C7. Oops, I keep writing A, but it's my A in this one is a 2x to the power of N minus K, so 14 take away 7 is 7. And my B value was a negative 3y to the power of 7. So another thing that you might have noticed here is, so this, my power was a 14, my powers ended up being 7s here. So you could even just take whatever your power is, divide it by 2, and that becomes your K value. Okay, in these last two examples, I didn't actually complete them because we're not going to come across a question like this specifically. What you can do by looking at this is just, you can figure out if x is to the power of 6. No, I'm not even going to go into it. Sorry, I'm going to stop there. If you want to know how to do these, or if you come across a question with them, then I'll go over them, but otherwise it just gets a little bit too confusing. Okay, so that is all for this section and for the chapter. Good luck.